Chapter 4, Section 30. Deduplication, Part 2. Duplicate detection by machine learning. Duplicate detection is an important step in data preprocessing, particularly when records contain inconsistencies such as spelling variations, missing information, or formatting differences. Traditional exact matching methods fail in such cases because they require perfect similarity between records. Instead, fuzzy matching, which calculates the degree of similarity between text or numerical values, provides a more flexible approach. However, fuzzy matching lacks the ability to adapt dynamically to complex datasets. This is where machine learning techniques, classification, and clustering enhance the duplicate identification process. One common way to leverage machine learning for duplicate detection is through classification, a supervised learning method. This method treats duplicate identification as a binary classification problem, where the goal is to predict whether a pair of records refers to the same entity. The process follows three key steps. Feature engineering. Various similarity measures are computed for relevant fields such as Levenshtein distance for names, Jacquard similarity for categorical values, and numerical differences for numerical fields. These features form the dataset for training the machine learning model. Model training. A classification model such as logistic regression, decision trees, or random forest is trained on labeled data, where pairs of records are manually marked as duplicates or non-duplicates. The model learns patterns from historical duplicate records and generalizes these patterns for new data. Prediction and decision making. Once trained, the model evaluates new record pairs and assigns a probability score indicating whether they are duplicates. By combining multiple similarity features, classification-based approaches reduce false positives and improve accuracy compared to rule-based fuzzy matching alone. Classification is effective when label training data is available, but it requires manual labeling and may struggle with large unstructured datasets. This is where clustering-based approaches offer an alternative. Unlike classification, which requires labeled data, clustering is an unsupervised learning technique that groups similar records together without predefined labels. This approach is particularly useful when dealing with large datasets where manually labeling duplicates is impractical. The process generally involves the following steps. The first step is representing features. Each record is transformed into a feature vector based on its similarity scores across multiple fields. The next step is applying clustering algorithms. We can use various clustering algorithms. K-means clustering can also be applied, though it requires specifying the number of clusters in advance, making it less flexible for dynamic datasets. Hierarchical clustering groups records based on similarity measures, forming clusters of potential duplicates. Density-based clustering methods like dbScan, density-based spatial clustering of applications with nodes, identify clusters of similar records while filtering out distinct entries. These algorithms are detailed in later lectures. The third step is duplicate resolution. Once clusters are formed, records within the same cluster are flagged as potential duplicates. In this step, we can apply business rules to determine which records to retain, merge, or modify. For example, If a dataset contains multiple entries for the same customer but with slight variations in spelling, clustering can group these entries together. Using these clusters, we can implement manual review or automated resolution. As an example of duplication detection by classification, let's see an example of how to detect duplicates using fuzzy matching and logistic regression. First, import the required libraries. In addition to pandas, import train test split from sklearn model selection. It is used to split the dataset into training and testing subsets. It is required to implement supervised learning. Next, import logistic regression from sklearn. Next, import accuracy score from sklearn metrics in order to evaluate the model performance based on accuracy. Finally, import fuzz from fuzzy wuzzy so that we can compare partially similar text fields. Let's use this dataset as an example. Here, we formulate duplicate identification as a binary classification problem, where the goal is to predict whether a pair of records refers to the same entity. So, this dataset consists of pairs of records, name 1 and name 2. We can see for each pair, the names in these columns are similar, but not exactly same. The third column, is duplicate, represents whether each pair is duplicate or not. 0 means not duplicated, and 1 means duplicate. First, let's implement feature engineering. This step applies fuzzy string matching to compute the similarity score between two names. The function fuzz ratio calculates the Levenstein distance, a measure of how many character edits are required to convert one string into another. The function apply iterates through each row and computes the similarity score for name 1 and name 2. Higher scores indicate greater similarity, making them useful features for classification. Next, let's prepare data for training. X is a feature data that contains only the similarity score, which will be used to train the model. Y is the target variable, which represents whether the names are duplicates or not. Next, split the data into training and testing sets. The dataset is divided into training and test data. By specifying the argument test size is 0.2, 80% of the data will be used for training, and 20% will be used for testing. Next, train the logistic regression model. First, initiate a logistic regression classifier. Name the model by applying sklearn logistic regression with empty brackets. Next, apply fit method to the training data to train the model. Finally, make predictions and evaluate the model. Apply predict method to the X-test data to classify name pairs in the test set. Then, apply accuracy score function to calculate the model accuracy. The accuracy is displayed as a floating point number rounded to 3 decimal places. It shows that the logistic model perfectly predicts the results. Next, let's see an example of detecting duplicates by clustering method. Here, let's see an example of using fuzzy matching and k-mean clustering. First, import pandas, TF-IDF vectorizer, and k-means. TF-IDF vectorizer is a function that converts text data into numerical vector using TF-IDF, that is, term frequency inverse document frequency. A TF-IDF represents the importance of words within a document. In this code, it transforms the employee names, which is text data, into a numerical vector so that they can be processed by the kmeans clustering algorithm. Kmean is a function from sklearn used to implement k-means clustering, a machine learning algorithm that groups data into clusters based on similarity. It is used to cluster the numerical representation of names, grouping similar names into the same cluster to identify potential duplicates. Next, let's see a sample dataset. It appears to be a data for 6 employees, but the top 3 and the bottom 3 might be the same person. In other words, these could be potential duplicates. These similar cases are not completely identical, but one of them contains a spelling mistake, so they actually represent the same entity. Next, let's convert employee names, which is text data, into numerical vectors and apply k-means clustering to group similar names. First, apply TF-IDF vectorizer to transform the names in DF name into numerical vectors. TF-IDF is a method that converts text into vectors while considering word importance. This transformation allows the names to be represented numerically, making it possible to compare their similarity. Next, define a number of clusters for the k-means algorithm. This means the algorithm will try to group the names into 2 distinct clusters based on similarity. The number of clusters can be adjusted depending on the dataset. Next, initialize the k-means clustering model. Random state equals 42 ensures reproducibility by fixing the random sheet. N-unit equals 10 runs k-means 10 times with different initialization and selects the best clustering result. Next, using fit predict, cluster the vectorized names using k-means. This operation assigns a cluster number to each name and stores it in DF cluster, so similar names are grouped together. Next, organize and display the data after applying k-means clustering. Sort the data frame DF based on the cluster column in ascending order. This groups similar names together, making it easier to analyze potential duplicates. Stores the sorted data frame and then displays it. John Adams, and J. Adams are in the same cluster. This indicates that these names are highly similar and could potentially refer to the same person. Mary Johnson, and M. Johnson are grouped together. This suggests that these names are variations of the same person. As we can see, we can use both classification and clustering to detect duplication in complex data. Classification can achieve high accuracy with label training data because it can learn complex patterns. However, it requires label training data, and it is less effective for large, evolving datasets. Clustering does not need labeled data, and it works well for large datasets. However, it may require fine-tuning to avoid over-clustering or missing duplicates. For example, when we use k-means clustering, we need to specify appropriate k-value. In practice, a hybrid approach is often the best solution. Clustering can be used to generate candidate duplicate pairs, which are then fed into a classification model for more precise decision-making. By integrating fuzzy matching, classification, and clustering, organizations can effectively detect and resolve duplicates, ensuring data quality while reducing manual effort. Thank you for watching. Please thumbs up and subscribe to my channel.